Welcome back to STEM Online Academy. All right. Today we're going to be discussing why a particular series can equal any number. Okay. So we're going to look at a series that you've probably seen before, an infinite series, but we are going to solve it uh, doing something very interesting, an interesting theorem here. Okay. And it's more complicated than it looks when it comes to analyzing the behavior. Actually, it's very complicated. But I'm going to simplify it into terms in which the language I'll be using will make it much more conceptually understanding. Okay, so we're going to look at this series right here. Okay, that's our question. Okay, we're going to look at this specific series right here and take a moment. It turns out, take a moment to think if it converges or not. Turns out it does. Okay, it does converge, right? So this series does converge, okay? And yet, by rearranging its terms, you can make it equal any real number you want, okay? So any real number, okay? Doesn't matter. It could be 0, 5, pi, -10, okay? Doesn't matter what the number is, it will converge. Same terms, just different order, all right? Same terms, different order, okay? So, I just want to note that out, right? If that sounds impossible, then good, right? That means you're thinking like a mathematician, okay? All right, so let's look at the problem, okay? This is an alternating harmonic series, okay? This series here is an alternating harmonic series. You've probably seen that it converges because the terms decrease in magnitude, okay? And they'll alternate in sign, okay? I think you can agree, decrease in magnitude, but alternate in sign, all right? So, so let me just show you something here, right? Let me just write out. What I'm going to do is exactly that, right? So decreases. So I'm going to say here, right? Note some characteristics. Decreases to 0, okay? And also another characteristic is that it's alternating. So alternating. So alternating, okay? And this would mean that it's going to converge. I'm going to explain the logic below, don't worry. So the natural assumption is once a series converges, its sum should be fixed. And that assumption is actually wrong, right? If a series converges, it doesn't mean that the sum is going to be fixed at all, right? Right? So let's answer a very important question that a lot of you probably would have trouble, most students would have trouble with, not just students, but anyone who wants to learn this stuff, right? The main issue at hand, right? The struggle, okay? And that's when we have to separate the terms, okay? Students have trouble separating the terms here, okay, in terms of analyzing the behavior, all right? So let's look at that. Let's look at separating those terms, all right? So I'm gonna write that here, all right? So let's use yellow. All right, so we got our infinite series here. So n equals 1 to infinity of -1 to the n. I'm gonna make this better. N, okay, so second, -1 to the n. -1 to the n, all over n, okay, over n. And this is going to give us, starting at n equals 1, right? What's that going to give us? That's going to give us -1 over 1, right? So -1 over 1, uh, -1 over 3. Let me see if that one is 3. If we had -1, yeah, -1 over 3. -1 over 3, -1 over 5, plus dot, 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 right? Because you have an infinite series here. Dot, dot. right? And then we have minus. Break this in terms. We got minus 2. This is going to be, this will be plus 1 over 2, right? Because when n is 2, I just group these really fast. 1 over 2, 1 over 4, right? 1 over 4, 1 over 6 for even terms. They're all positive, plus dot, dot, dot. Okay, right? Right, even terms, we have all positives. And for odd terms, when we have n is an odd exponent, we should be getting negatives, right? Because negative 1 to the 3, when n is 3 over 3, right? Negative 1 over 3, 5, negative 1 over 5, 1, negative 1 over 1. Okay, so this is what we've got right now. Looks pretty cool. Okay, both of these are going to diverge. Okay, so both, let me highlight. So both will diverge. Okay, I like that. Both parts of the expansion will diverge. Right, so let me just circle both sums here. Okay, so let me just do this. Both of these will diverge. Okay, so individually, right, they'll blow up. Okay, together they balance, but just barely, and that balance actually is unstable, and that instability is the entire story when it comes to the series. Okay, right? So I hope that helps with the main struggle that you may be having when it comes to understanding series. Okay. Now the key idea for evaluating this is conditional versus absolute convergence. Okay. Now you should already know that this series converges, but not absolutely. The series converges, but not absolutely. Okay, so let me write down here. Okay, so I'm going to write something else. Okay, so we're going to say that it converges, but not absolutely. We have to take the sum from n equals 1 to infinity of the absolute value, negative 1 to the n, all over n, right? Okay, we have to take the absolute value of it, all right? And then this is going to be equivalent to the sum from n equals 1 to infinity of 1 over n, okay? Automatically, this would equal to infinity, all right? That single fact changes everything, okay? This single fact right here changes everything, because you can see that there's some sort of divergence, okay? Right? Absolute convergence locks the sum in place, but conditional convergence does not, okay? Remember, absolute convergence locks things into place. Conditional convergence does not, all right? Okay, so let's look at how this rearrangement works, okay? How this exact rearrangement works. So I'm going to go to another page here, okay? We're going to use something called the Riemann rearrangement theorem. There's multiple ways to solve this problem. One unique way is using the Riemann rearrangement theorem. Okay. So suppose I want the sum to equal to 5, right? So I'm going to say the target number is 5. Okay, so let's say our target is 5. Zoom in on. Okay, so let's say our target. Oh, sorry, shouldn't say that. Let's not do the target number yet. I'm going ahead of myself. Okay, so if you want to use the Riemann, we're talking about the Riemann rearrangement theorem. So the Riemann rearrangement theorem states the following. Okay, I'm going to write here Riemann rearrangement theorem. I think you get the idea. It's like Riemann rearrangement. It states the following, right? it states that one, okay, if, right, so if a series, okay, this is very important to know, converges conditionally, converges, converges conditionally, so if it converges conditionally, if it converges conditionally, then for any, so then for any, for, I'm going to highlight this, any, in my point home, or any real number, right? Real, okay, real number, any real number, I think we can make that smaller. We don't have to emphasize that. Any real number, yes, one sec. Then he's the most important. Any real number, right? For any real number called capital L, right? So let's say called capital L. For any real number capital L, you can rearrange, right? So you can rearrange. You can rearrange the terms. You can rearrange the terms so the series converges to L. Right? So the series converges, right? Converges to L. Okay? This is a theorem. Okay, this is a, I'll say THC or M somewhere. All right, so I put theorem. Theorem. I'll put it here. It's not a room. THERM. THRM. That bothers me. I want to say THERM. Okay, that's the Riemann rearrangement theorem. So take a moment to absorb that, let it land. The idea is shockingly simple. Shockingly simple. Okay? It's very easy, actually. Okay, so let's look at, for instance, suppose I'm going to show you how the Riemann rearrangement theorem works. Suppose I want the sum to equal 5. Okay, let's make our target 5. Okay, so target. Okay, so target. Sec here. So target. Target is 5. So the target number is 5. Okay. What you do is you're going to start adding positive terms, right? Until the partial sum goes above 5. Okay. So again, what I want to do is I start adding the positive terms. Okay. Right, so I add positive terms until the partial sum goes above 5. Right. Right. So this guy right here. That's what I'm talking about. So a sec, let me put okay. As long as we 5. Okay. Then I add negative terms until it dips below 5. Okay. So I made that crossing arrow up to show that I'm going above 5, and then another arrow down to say that I am having a dip. So again, what you do is first you start adding positive terms until the partial sum goes above 5. Then you add negative terms until it dips below 5. Okay. And then positive again, and then negative again. Each term is smaller than the last, right? So the overshoot gets smaller every single time you iterate. Okay. Okay. Eventually, the sum settles exactly where you want. Okay. That's what's going to happen. Right? Right? So you may be asking why this does not violate any form of logic, because it is a strange way to approach this problem, this theorem, anyways. Okay. Because nothing illegal happens here. There's no violation. There's no violation of any type of mathematical properties, right? We didn't change the terms, okay? We didn't change their values, right? In any of this in our series. We're only just changing the order, grouping the orders, okay? And because the series is only conditionally convergent, only the order matters, okay? Again, wait, since the series is only conditionally convergent, the order matters, okay? And this is why the rigor matters, right? Not to be pedantic, but because the intuition fails quietly. Okay. Now let's go look at any applications of this type of problem here, right? Also, I want to show you in terms of something else. Another way I can say this here is that you would have an oscillation of, let's say, for instance, you can make a curve to show you geometrically what's happening. So there's an increase, right? And there's a dip, then there's an increase and a dip, right? Some sort of oscillation, all right? Just to be a visual what's happening here from earlier. But anyways, let's continue, right? So why this matters, right? What is the applications of a problem like this, okay? Right? This idea shows up everywhere in nature, actually. Okay. First off, we'll talk about a mathematical application to Fourier series, okay? Right? This series, right? This specific series uh, comes in comes up in Fourier series. Okay. In Fourier series, rearranging modes can change the convergence of the behavior. Okay. I won't get into modes. Modes um, has to do more to do with waves. I'm not going to get into that as much, really, but I hope you get the point. The Fourier series is an application. Okay. Right. Now, that's when it comes to Fourier series where this series would pop up. Now, in physics applications, right? It would explain why you get something called a regularization scheme, right? So regularization schemes, for instance, that would be another application of this particular series, okay? And then finally, what we're already doing, which is in calculus, it tells you exactly when you're allowed to manipulate the infinite sum safely, okay? So it's a uh, very important approach, the Riemann rearrangement theorem, when it comes to analyzing a series. Okay. All right. All right. Just I do want to mention something, right? If you're a strong undergraduate or an undergraduate in general, doesn't matter. An example like this almost makes sense, but not quite. Then that gap is exactly what my book, Advanced Integration Techniques, is written for. Right? It's a calculus book. Okay. And if this kind of reasoning is blocking your grades, right? I also work one-on-one with students. Okay, the links will be below in the YouTube description. Okay, so watch out for those links below. They'll be in the description. Okay, right. So the lesson here is simple, right? I want to write one more thing that is very, very important. Okay. right over here. Okay, lesson is very simple, and that is convergence. Okay, convergence, convergence, convergence is not enough. Right? Is not enough. That's very important here. Convergence, it's by itself is not enough. Okay, it's not enough. Highlighting this because it's very important. Okay, convergence is not enough. It's the structure that matters. Okay, structure. Use a different color here. Structure is what matters. Structure matters here. We're in convergence. Okay, structure. Okay. And once you see that, analysis stops being mysterious and starts becoming powerful. Okay. Hope you guys enjoyed today's video. Stay tuned. There'll be more interesting calculus, ODE concepts, and physics concepts coming soon. Have a great day, guys. Bye bye.